Okay, let me start the class. Today I'm going to explain about practice of offline reinforcement learning with robots. In today's lecture, we are going to implement the reinforcement learning in the robot. We first collect the data set from the robot and train in the Colab server, and again move the weights into robot and inference. So first, let me explain about what is the difference between offline reinforcement learning and online reinforcement learning. As the previous lecture, online RL and offline RL can be divided by how the policy or whether the policy interacts with the environment directly or not. In online RL, the policy learns by interacting with the environment and collecting data while training. So it can handle changing environments with adaptation, even if the dynamic states are occurs, and the policy learns when what states occurs when I do some actions. But it is difficult to train when the interaction with environment is costly or dangerous, like in robot control or autonomous driving. So in particular, the famous representative online RL is like DQN, PPO, A2C, or SAC, which you guys heard about that. But it can interact with environments, but it has those limitations. However, offline RL learns a policy from a pre-collected dataset, so it doesn't interact with environment directly. Strength is it is safe and cheap to train the policy and leverages large logs like driving or robotics. So it can use just dataset collected from other users or previously. But it has also a limitation called distributional shift problem. The learn policy may take actions not well covered in the dataset, which means the dataset uses behavior policy, and when the dataset doesn't have the state and the real policy meets that state or unexpected condition, it can overestimate the value functions or output wrong actions. Because the dataset sometimes uses like random policy or expert policy. So the dataset tends to output high rewards from many states. So the policy can learn that for almost situation, the states output so high rewards, but it is not true. When the action is not output well, the reward should be low, but it can overestimate. That's the distributional shift problem. There are some examples like behavior cloning, CQL, and IQL. We are going to implement and run IQL or behavior cloning. And behavior cloning is actually not kind of reinforcement learning because it doesn't use reward. It doesn't maximize reward, but regression. It uses regression to state to action. So let me explain about IQL, implicit Q learning, briefly. IQL tends to prevent the overestimation of the policy. So it estimates the upper bound with high expectile of the Q function. It uses like this. The mathematical expression called high expectile. So it tries to prevent overestimation via expectile regression. And to learn a policy, it learns implicitly from the Q function, not using the like maximizing the Q function or explicitly get from the action. It uses the expectile and implicitly learns. And for each state, this upper bound is the conservative baseline so that the agent toward action supported by the data and away from out of distribution actions. I'm not going to explain about the loss and the mathematical theory in deep, but the tendency of IQL is to keep estimates close to the data distribution and also reducing overestimation and improving the stability. And let me explain about the file organization and what to download, what to run. First of all, we are going to move across the robots and collab. So first, listen to explanation and then follow them. First, in robot, we collect and save data with the keyboard using that collect teleoperation data Python file so that we can get the teleoperation data set directory and the pickle file. We can test the data file with play teleoperation, but it is not mandatory. And next, we copy these data sets into collab and using the IQL package and train IQL Python file, we train a policy with IQL. Then it outputs the policy weights, PTH file. The model parameters will be created. And then we again move this weights file into the run IQL. We move into the robot and load the policy weights file and run the run IQL Python file, and it will interact with the robot and control the actual robot moves. Briefly, how it takes state and how it output actions. It gets state with X, Y, Z, and RPY and gripper state of consisting 7 dimensional vectors, and RPY, which means roll, pitch, and yawing. And also it outputs to robot action consists of the delta of X, Y, Z, RPY, and the gripper state, which means 1 to open and 0 to close. When the action is passed into the JetRover Gym interface, it converts into servo pulse so that the robot can move actually. And also when the servo pulse and image comes from the JetRover Gym, it converts into the state using the inverse kinematics and forward kinematics, which you guys implemented in prior weeks. So yeah, the file loads the model from IQL and the parameter of the policy from results. Real-world interactions will be repeated. So let me start from the robot setting. We should install those packages outside of the virtual environment. pip install numpy, the specified version, and OpenCV Python. And from this practice, we are not going to use the RGB images. So we all commented the code that uses RGB images, as the training cannot converge fastly. So if you want to use RGB images as inputs, you should clone and download more packages and uncomment it and implement some codes. So you don't have to download the RGB images like R3 and backbones. Using robot, we should collect the demonstration. We use teleoperation to perform tasks and record trajectories consist of state, action, reward, terminated, truncated, and metadata. So whenever we input the action with the keyboard, it saves these pairs. So how to run the program? We go into the manipulation experiment, which you located the file in manipulation part, and run the collect teleoperation data, which is downloaded from today. And the data will be stored in manipulation experiment, teleoperation data set, and like this name. So how to use the collect teleoperation data? The UI looks like that. And in the last step, last line, it asks how action will be performed. We should input among those keys. Let's explain one by one. So when you input the space and press enter, it can toggle the gripper. When the gripper is open, it is closed and closed to open. R to reset and to save the current demonstration, which is saved from this trajectory so far. H to print health, Q to exit the program. Whenever you press this key, and you should press the enter. And there are also our main actions, WASD and ONL. It moves upward and downward, forward and backward, and rotate pitch, which means the gripper rotates in the clockwise and anti-counterclockwise. For those 6 actions, we can input multiple inputs like ASO, type ASO, and press enter. Then it will move left, above, and lifting the gripper at one step. So you can input multiple actions. So after training some amounts of data, you move into Colab, and in the Google Drive, there are some files. Download some folders, which is in like that. The teleoperation data set, which you guys collected, and IQL and trend IQL.ipynb. After opening the Jupyter Notebook files, the data set should look like that. Inside the teleoperation data set, and pick up cube or some task name. We should run cell by cell. So mount the drive and link the root from your directories and install some packages. And this here is the training part of learning IQL. So basically the IQL algorithms are implemented already, and you should change and tune how the hyperparameters work, like tau, this is temperature variables, or max time step, save frequency, or some things. Briefly explanation, when you modify the temperature, it will learn how randomly the policy will taken. So it means about the entropy of the policy. In the IQL paper, the temperature is 3.0. So basically it can learn with 3.0, but you should try another values. And also, in specifically, when you type temperature into 0.0, then the exponential part of the difference between Q and V becomes 0. So it doesn't learn about the real function. so it becomes the behavior cloning. When you're trying to learn a policy, you also can try this and maximum time steps to how far and save frequency to save the model parameters. After training, the files like that will be saved. And what you need for robot to infer is just this actor path file, not the value critic or optimizer scheduler. You just copy the actor file and move into the robot. And then turn back to the robot. We should set the proper path in the run IQL Python file. Move your file in manipulation experiment IQL results, but what else? And change the path of the file in run IQL.py. And when you run the Python file, and it will perform the action from the policy with inferencing with the current state. It is not video, so I'm going to show you later. And there are some tips to train and how to converge fast. First one is to fix the environment and then collect the data. In practice, the IQL dataset is needed according to how much variance of the dataset. So the QoS position relative to the robot should be fixed to make the dataset consistent. The most important part is to make consistent dataset. Do not put too much variance when you're collecting the data. Try to do some same actions every data collection. Even if you type the same actions, as it uses the servo motors and inverse kinematics, it has its own variance and uncertainty, so it can have some variance. Variance of the data makes the model more generalizable, but needs much more time and data to converge. The more variety of the data and the more data you need it. Train the model at least 500,000 steps. It takes about 2 hours in collab. So take care of the times and collect the data more than 5. In practice, we should need more than 5, but for now, when we collect the consistent data, 5 is enough, but the more data, then the more likely to converge the policy. Second tip is about modifying the manipulation in env.py in the inference phase. We can modify the gripper threshold variable. The robot manipulation configuration code is in manipulation in.py and adjust gripper threshold to ensure the robot operates correctly. The threshold means I said that the gripper is controlled by the value of 0 to 1. 0 is closed and 1 is open. But in actual inference, the policy can output the continuous value like 0.4 or 0.6. So we explicitly implemented the gripper. When the gripper state is upper than the threshold, it always open, and vice versa. So when you inference the policy after training the policy, when the policy tends to output the gripper action like 0.6, it seems to want to close the gripper, but the actually gripper is not closed, and then you can change this threshold. It is not about the training or policy, so you can change it later. Yeah, that's all for tips. For grading, this assignment is worth of total of 40 points. After you send the parameters, TAs will check your motor's performance in a real robot one by one, and we will evaluate the tendency of the robot's pickup behavior. The task is to pick up the cube, and it gets full credit if the arm goes down, gripper closes, the arm lifts, even if it doesn't actually grab the grabs the cube. So in this grading, we are going to see just the tendency of how the arm moves. It doesn't have to grab the cube accurately. So we just see these three components like in the following order. When the robot only goes down, it can get the 10 points, and it goes down and grip 30 points, goes down and up 20 points, goes down, gripper close, and when it goes up, it will get 40 points. And when the order is not correct, it will get no points, like go upper first and close the grips, like that. So trying to follow the tendency of the robot arm. You should submit the actor model parameters, PTH file, and any code you modified. When you modify the manipulation EMV file, then you should mention it or some other codes. Submission by email, one submission per team is sufficient to this, and deadline is for Friday class next Friday until, and no late submission allowed. That's it, and is there any questions so far?